Ladies and gentlemen, please welcome to the stage Head of Data Science Advanced Programs at Uber, John Peterson, and Head of Design Advanced Programs at Uber, John Badalamenti.
Am I on? Okay. I'm back, and this time I'm here to talk to you guys about a revolutionary update on this tool that we're building for the Uber Elevate network. So let's get started. Imagine knowing precisely how to design your city for trip demand that hasn't happened yet. Where do you fly? Where do you need hubs? How many hubs do you need? How far away should they be? How many vehicles will they need to support? How should we invest in infrastructure? Or imagine designing a vehicle equipped to serve your riders and their demand perfectly. What type of vehicle is it? How many seats will it need? How quickly should it charge? How fast should it go? How far should it go? What type of landing gear will it require? What about passenger loading or unloading times? You see, the answer to any one of these questions impacts the answer for all the others. But there's one thing every city has in common, is actually that every city is unique. But Uber is uniquely prepared to provide universal clarity. By understanding how people move, we can start answering these questions. Designing the VTOL network, confidently informed by Uber data, and not just theory. So with that, I'll pose a question to the audience. How would you go about answering this question? How would rider throughput and vehicle load factor be affected over New Year's Eve here in Dallas if you increase the recharge rate by 10%, put an additional seat in the vehicle, decrease the cruising speed by 20 miles per hour, increase time savings threshold by 15%, reduce the minimum ground time by 30 seconds with a moderate repo model? Ladies and gentlemen, I'd like to introduce to you the one man in the building who can help us answer this question, Head of Data Scientist, Dr. John Peterson.
Thanks, John. Thanks, John. Good afternoon. It's an interesting experience to see the look of fear on my colleagues' faces once they realize that a data scientist has commandeered the microphone. It'll be all right, guys. Relax. My job is to think outside of the VTOL itself. So the vehicle is the heart and soul of this summit, and that's only as it should be. However, we are interested in asking a myriad of questions about how many riders we can serve. We want to know what the vehicle utilization looks like. We would like to know how many riders we can get in a vehicle. And I believe it was in an investor panel, and if I'm not mistaken, it was Bilal who posed a very good point yesterday that it's absolutely imperative to integrate product thinking with technology. So we're going to answer some of these questions and many more in the next few minutes. So we have built a decision-making tool, which we call Flux Optimizer. Back to the Future fans, I hope that resonates with you. And this tool it's an optimization tool that has, I think, 3 specific use cases that I really want to focus on today. Number one is we want to know about the infrastructure itself. Where precisely should we place these vertiports? In his keynote yesterday, Jeff Holden announced some of the initial phases of the vertiport design and the route structure in our 2 launch cities. So these are not arbitrary. There's data and there's science behind that, and we're going to talk about that in some depth. We're not only interested in the lat and longs of these vertiports, but we also want to know how much infrastructure is required, how many parking paths, whether or not there's recharging capabilities, and other questions. Second, we want to try to the very best of our ability, really characterize the VTOL network. We want to try to understand how VTOLs are actually flowing throughout the system. We want to understand what the barriers are, what the bottlenecks are to increasing more riders and to eking out more efficiency. And so we're going to answer that in the second part. And then lastly, we want to try to have a feasibility study. We want to understand what it is exactly, what conditions exist for which this network to be healthy and sustainable in the short and intermediate term, as well as the long run. So those are going to be the three kind of classes of questions. We're going to look at a number of explorations later, but first I want to kind of open the hood and really look at this engine a little bit more in greater depth. And so you can think about this model as containing 4 decision-making modules. The first is demand estimation. So when we began this work some months ago, we did what made sense to us, and that's use what data we have. Naturally, Uber has got considerably granular data for a number of things, trips, where cars are, et cetera. But what we're interested in is we want to know where are people traveling to. And so what we have done is we have the user in the system specifies a given city and a radius from which we will fetch every single completed trip between a start date and end date defined by the user. And what we do is we look at the longer distance trips. So if you consider a trip that is 5 miles long, it is far less likely to be served in a VTOL than one that is 30 miles long, for instance. So we fetch all completed trips exceeding some minimum distance threshold defined by the user. DFW, it might be 20 miles, and it might be closer to 10 miles in Dubai, for instance. And we fetch all of those trips, and we proxy that for demand. Now, there are a number of shortcomings, admittedly, to using Uber trip data. Number one is, while we're nearing 500 cities, which is exciting, it is not quite as ubiquitous as, we're not in every city, and there are regulatory barriers. If we wanted to run this, for instance, in a market in upstate New York, we really cannot as of now. Secondly, the demand patterns in a given city may or may not be represented by Uber data. And so we have partnered with our colleagues at the firm SDG, and they are building out a far more intelligible demand model. But that same forecast can be fed into the subsequent 3 phases as well. So using Uber data, we have on the panel at the top is an Uber road network. So any road in blue corresponds to a road segment that was traversed by 1 or more Ubers in a 24-hour period. And this, I'm told, is a slightly out-of-date figure. It's always fun to watch this expand. So that gives us total trips in a given day. The figure at the bottom shows the specific pickup and drop-offs of these long-distance trips in a 3-day period here in DFW. These are all trips within 120 miles of the center of Dallas that exceed 20 miles, for instance. So we have an idea of where people are traveling. The next question is to try to identify specifically areas within the DFW area that we want to consider building out this infrastructure. So we take the previous chart that I showed, the pickups and drop-off locations, and we run a very simple k-means clustering algorithm on those to try to find what I like to call a candidate hub or a candidate vertiport. So the red dots are centroids of these clustered regions. We usually use a number of approximately 100, somewhere between 100 and 150, but we also allow the user the ability to input specific properties as well. So we have this partnership that was announced yesterday. We've got a wonderful set of partners at Hillwood Properties, and so if they or another real estate developer was interested in trying to run the same model, they are able to do so from properties in their portfolio. So it's completely flexible. So we have an idea of where people are traveling. We have an idea of where it might make sense from our data to operate. The next question is, what do we choose? And so I'd like to, first of all, consider a simple example. Consider a long-distance trip between downtown Fort Worth and Dallas Love Field. So what is absolutely at the core of Uber is saving people's time, giving people their time back. And so this is one of the kind of product-related questions that we're posed with and that we have to get very rigorous on very soon. And that is, when do we consider someone taking a VTOL? Should their time savings exceed some threshold, or what would that look like? And so we're taking the standpoint of trying to save people time. And so if you consider this particular trip, they can either take a VTOL or not. If they do take a VTOL, there would exist a pair of vertiports, a departure vertiport and an arrival vertiport. They would get in their Uber, travel to the departure vertiport, They would fly, which that time would encompass the ascend, descend, and cruise, and then there would be a car waiting for them, taking them to their final destination. So if you take each one of those time components up, we get an estimated VTOL time, the time of an itinerary that is represented by a passenger's origin, destination, departure, and arrival vertiports. And we can take the difference between it and an estimated ground time as well. And so that difference gives us how much time is saved for that particular itinerary. So the panel on the left, for instance, would show a candidate itinerary for which we'd probably discard due to this inconvenience that's incurred in that last segment where the rider departs from downtown Fort Worth, and here we send them to Frisco Station, and they want to go to downtown or to Love Field. So it's almost certainly that there's going to be too much inconvenience for that route, so we would not consider it. However, on the next panel, this is one which there is considerably higher overlap, for which we would probably consider that as a valid itinerary. So again, we consider an itinerary to be valid if the time saved exceeds some user-defined threshold. We typically like to say around 40%, 50%, 30%. It really depends on the market as well. But for now, think of time saved to be 40% relative to a ground trip. So the question is again, which subset do we pick? And I believe it was Professor German earlier today who said something about, I think it was a sea of combinatorics. Well, we have oceanfront property in that case. And so this is the output of one of the models. If the user selected 15 or 20 hubs, for instance, this would give an Uber network. And so again, the problem here is to find the subset that achieves some objective. That objective could be to move as many riders as we can through the network, saving at least 40% of their time. It could be to maximize the total time savings by locations of these specific vertiports. So this gives the solution for DFW. So once we have the actual network itself, the next question is how do these VTOLs actually flow throughout the network? And how sensitive are key first-order metrics to various assumptions that we're making? So we built a VTOL route optimization engine as well, which constitutes the fourth component. So again, what we take as given is trips, and we take as given where these individual hubs are. Now the question are, how should these VTOLs fly? There are a whole slew of questions that we have to answer. One question, obviously, is what is the sequence of vertiports that these VTOLs traverse? Another question is how do we assign riders to specific VTOLs? Another question is this very interesting trade-off between saving riders as much time as possible, or do we hold the VTOL, hold the departure some period of time and allow more riders to share the vehicle? So product decision, again, we'll talk a little bit about the importance of sharing the vehicle later, but for right now, that's a very interesting kind of trade-off. So this is a very this is a spatial and intertemporal decision as well. Another decision is to decide about deadheading. So formally, a deadhead is when we define a deadhead to occur when there's no passenger. And deadheads can occur either to pre-position the aircraft to fly another rider from another vertiport, or potentially to get out of the way of an inbound vertiport, of an inbound VTOL, to free up capacity at a given station. That's another question. The question about battery recharging is another one. When do we actually charge the battery? How much do we recharge for future flying? So these are all questions that this VTOL route optimization model will answer. So a specific output might be carrying 2 passengers from Frisco Station to DFW, maybe another passenger from DFW to Fort Worth, and then flying to downtown Dallas in the third segment. So that would be an example of an output. So we've gone under the engine a little bit, and I would happily occupy more time. So if anyone has questions specifically, I'll be happy to answer those either in this session or elsewhere. What I really want to do right now is kind of dig through some of the specific use cases, and we're going to start with this hub optimization engine. Mr. Holden yesterday revealed what this network in DFW may look like, and so this is how we arrived at that. So again, we're taking trips from a 3-day sample, all completed trips within 120 miles of DFW. We do our clustering using 100 candidate vertiports, and we obtain a figure at top. We run it through this hub optimization engine, and we obtain a network at the bottom. And so just recall that these areas, these hubs that we're choosing, they're somewhat arbitrary lat longs. These are just centroid of these clustered regions. So as I believe it was Mr. Pro aptly said yesterday, everyone needs real estate developers. Elevate is no exception. So we worked with our exemplary partners at Hillwood and tried to closely match properties in their portfolio to properties that we're recommending from our optimization framework. And so we obtain a network, a portfolio of the Hillwood properties that are seen in that photo, which are the blue dots. So now we have this Hillwood network, and now the question is, how do we actually build out this infrastructure across time and space? So we start out incrementally, trying to build out a handful, maybe 2 or maybe 3 vertiports initially, and then eventually expanding them. And so the first figure on the left shows what the 2-hub solution looks like in DFW. This is how we attained the solution that the initial route between Frisco Station and ideally the DFW area. We heard earlier this morning about the importance of DFW and the volume of trips, so it's not surprising potentially that we would opt for this route. So we start with those two hubs, and what we notice is that we can cover, just with 2 hubs alone, 15% of long-distance trips in the Metroplex, which is higher than we thought given the vastness of the area. Other cities, it's typically a little bit higher. So the next question is, what are the next 3 incremental hubs? And again, we fix those 2 hubs. We want 5 hubs returned. It finds 3 new hubs, and those are located in downtown Fort Worth, downtown Dallas, Victory Park, and Las Colinas, which is not too far from the airport. And what we find is just with those 3 incremental hubs, we go from 15% of rider coverage up to 42%. And we repeat this exercise going on to 10 vertiports, which gives us nearly 50% of trip coverage, long-distance trips. We've repeated this exercise in a number of other cities, Dubai included, obviously. And the specs are a little bit different. So Dubai, we're not looking at 20-mile trips. Now we're looking at 10-mile trips, much shorter distance. It kind of makes sense given the demand patterns are a little more concentrated in Dubai. It's a little more favorable to us. It's a little bit smaller region. And what we find is that with 10 miles, now again, I'm just going to reemphasize that 10 miles, shorter trips, it's considerably more difficult to achieve that 40% savings because you have these ground segments at the start and end of the journey. So if we looked at 20-mile trips, we can cover over half of the trips in Dubai, but we are thinking about shorter missions. So with 2 hubs in Dubai, we can save at least 40% of time with nearly a quarter of all itineraries, a quarter of all trips in Dubai. In the first route we're looking at or are interested in using automatic clustering is the downtown near the Burj Khalifa, the world's tallest building, and the Jumeirah Beach area. There's considerable value of going to 3 more hubs where we can save already over half. And ultimately, we're looking at 50 hubs where we can save pretty close to 90%. We can cover roughly 90% of all trips, saving 40% where a trip is, again, 10 miles or over. And if anyone wants to go to Abu Dhabi as well, we're building out Abu Dhabi in a subsequent phase. We've run this in other cities, Singapore, for instance. And so Singapore is interesting. If we wanted to cover trips exceeding 20 miles, we can get nearly all of them between the airport and kind of the west side of the island. That's not surprising, given that Singapore is not much more than 20 miles long. So again, we're looking at, I believe, 8 to 10 miles. We've run a number of different experiments. Typically 8 miles is generated by these figures. So if we look at all trips that are at least 8 miles long, we can cover about a quarter of them, saving 45% time in Singapore, where the first 2 hubs ideally would be the Singapore airport and the central business district. And if we were to expand these, roll out these hubs gradually, not surprisingly, they would just kind of go around the perimeter of the island. We've run this in our hometown of San Francisco, primarily because I have a dream of going from my house to Monterey in 15 minutes. And then Las Vegas. We've run this in a number of other cities as well, but these are what some of these networks may look like. So now the next set of experiments I want to run are on this VTOL routing engine. So we we're pretty confident that we can ascertain what these networks might look like. But again, how do these VTOLs perform? What are the metrics? What are the drivers to serving more riders and finding more efficient routes, for instance? And so the VTOL routing optimization, what I'm going to do is we're going to spend some time stating clearly what the assumptions are, and then we are going to kind of relax these one by one. We're going to turn some knobs, and we're going to learn about their sensitivities. So we're going to start in Dallas, and we're going to look at 5 hubs. So again, I just want to emphasize that we're looking kind of the short to intermediate term initially with 5 hubs. These are the 5 hubs in the Hillwood network. We consider an airspace separation of 2 miles, meaning that any 2 vertiports must be at least 2 miles apart. We're looking at eVTOL ranges between 20 and 120. That 120 miles, not really binding. We also consider a constant ascend and descend time of 75 seconds and 45 seconds, respectively. So some of the knobs that we're going to configure. First of all, we're going to ask a very obvious question: how many eVTOLs do we really need to serve the demand? But we're going to consider a vehicle with initially 4 seats, 1 seat for the pilot, 3 for riders. We're going to consider a 5-minute minimum ground time. Again, this is the time between departures and arrivals, departure I and arrival I-1. We're going to consider an en route cruise speed of 170 miles per hour. Sorry, international friends, we should have done that, but we're over 300 kilometers per hour. We've already heard from our partners, ChargePoint, who we heard yesterday from Pat, their CEO, who said that it takes roughly 15 minutes to go from, I think, 25% to 90%. We're considering 20 to 90%. And then I'll talk about the trip volume a little bit later. And again, I just want to be crisp here. Any time an itinerary is generated for a rider, it must save at least 40%. And then we're going to look at how this compares to maybe shorter trips in Dubai, and we can talk a little bit about other cities as well. So knob number 1 is how many eVTOLs are needed to satisfy the demand. So from the output of the hub optimization, we've got a number of hubs, and each hub is characterized by a number of pads. So what we do is we change the share of VTOLs needed with respect to that capacity. So hypothetically, if we had 100 hubs and we were interested in 35%, then it's like 35 eVTOLs. So we vary this number from 20%, 30, 40, and then we'll go up to 100%. And what we see is it kind of plateau around 40%. So initially, and again, I'm going to emphasize this is an early stage. There are many knobs we're going to turn. If we had higher trip volume, it flattens out much later in the curve. But initially, with this data, we believe that we need approximately 40%. The number of eVTOLs should be about 40% of total capacity, total eVTOL capacity. Not surprisingly, that when we have more aircraft, the average load factor, average occupants per mission, goes down. And we're going to talk a little bit about deadheading later again. How often we deadhead, that's kind of one metric of interest. So just to recall, 40% of total eVTOL capacity in the network we're going to use as our new benchmark figure, and initially we have a load factor of about 1.55. Just talking a little bit about why load factor is important. Again, it is absolutely central to our business model and to our vision to make Uber as reliable as running water everywhere for everyone. And so having worked on our Uber Pool product for a couple years, if you're not familiar, Uber Pool is the service that we offer whereby riders can share the car with other riders heading in approximately the same direction. What we find that's so important is this, what I might refer to as a liquidity imperative. This is the idea that if we can bring that price point as low as possible, we stimulate more demand. And as we stimulate more demand, we can be far more selective about how we're assigning riders into individual seats in eVTOLs. And that's important because when you have more possibilities to make matches, you can find more efficient matches, thereby saving more, thereby bringing the price down even further, and just kind of perpetuating this flywheel effect. So load factor is something that we're going to consider quite rigorously. And so initially we're getting, again, 3 riders for every 2 flights approximately, which at the early stages. So the next thing is how many seats do we actually need? So again, we're going to assume, we assumed 3 seats in our baseline. Let's kind of vary that. So as we increase our seating capacity, not surprisingly, we see kind of diminishing marginal gains from having more seats. And again, at least in DFW, it does flatten out around 3. So loosely speaking, we think a three-seat vehicle is kind of a target, might be a potential target initially. Not surprising, the load factor is increasing, and then the utilization, as you permit more riders in a particular VTOL, then you can cover the demand with fewer VTOLs, potentially leading into a reduced utilization. So just kind of focus on those specific routes for which have higher capacities. The two routes that we're flying more and more people together, we believe will include Frisco Station and DFW, not surprisingly, as well as Frisco Station to downtown. What's interesting is even though the number of trips by VTOL is not necessarily is not necessarily very high between Frisco and Las Colinas, which is close to the center. It's the center. It's a little bit southeast of the center. Even though the number of missions is relatively low, it tends to be that those missions, it's likely commuters. These are people that are going at the same time, so we can kind of get more very rigorous term like we like to call butts and seats. Also, DFW to downtown Fort Worth, we have a relatively higher load factor as well. So next is minimum ground time. So you may have seen Mark Moore's enthusiasm yesterday when he was talking about the impact of minimum ground time, and there's good reason for that. So we assume initially a 5-minute minimum ground time at every vertiport for every mission. And what we find is that the value of just reducing this, even just somewhat marginally, has considerable gain in throughput. So what we find is going from, let's say, 5 minutes. Suppose we live in a world where we can reduce it 3 minutes. We find that we can increase our total rider throughput by about 35%. Which is pretty substantial. What this means is that there are a lot of riders kind of on the margin, kind of close to that 40% line. Not only that, but you also give riders better experiences. When you can turn around a vehicle faster, you naturally can save more time because it spends less time on the ground. And also, again, we see utilization really increase as we lower this. So when we permit fewer, shorter, faster turns, these VTOLs are taking advantage of it. What's interesting is your hub structure actually might change a little bit in a world where you can turn eVTOLs faster. So what we saw on the left panel is this is our network that we presented. The panel on the right shows what a network might look like with a 2-minute reduction in the turn time at a given station. And you'll notice that the network is pretty similar, but we're actually deleting a node at Las Colinas and we're inserting one in North Denton. Which is pretty interesting. The intuition, I believe, behind that is we can serve a lot of the riders, the same riders who were previously flying into Las Colinas. We can serve them by flying into DFW because they're getting there a couple minutes faster. So presumably, we can still serve a lot of number of riders through a different hub, and we can open a new hub, giving greater marginal value. Next up is we want to kind of look at airspeed. And so we saw a very compelling talk this morning from Professors McDonald and German. And what we want to do is to vary en route speed. So again, we're using 170 miles as kind of a benchmark. So the question is, what kind of value can be attained by faster or slower eVTOLs? And so the value of getting an additional 30 miles per hour on average results into about an 18% increase in rider throughput. Conversely, if we were to go below, we find also approximately an 18% reduction in rider throughput if we went from 170 to 150. What we find is that with, at least in the DFW area, where we're flying a little bit longer missions, at least 20 miles, the share of trips that we can actually cover to save 40% is negligible in DFW. We're saving fewer than 1% if we're flying at 50 miles per hour. Naturally, in other markets where we're flying shorter missions, then perhaps a reduced airspeed, a reduced cruise speed is a little bit more amenable to those type of cities. Not surprisingly, you fly faster, you get higher load factors because you get more matching opportunities, and also the rider experience as well is better when you can fly faster. So much like we saw in the preceding knob we were turning with the minimum ground time, now we're interested in exploring what the network might look like if we could fly at 200 miles an hour. We checked this at 150 miles an hour and even 100 miles an hour, and we get the same network. But interestingly enough, if we can fly faster, then we get a slightly different network. And I think this is quite intuitive, right? So we see the same phenomenon where we delete the Las Colinas hub, presumably, again, because we can serve much of the same riders through DFW. And now, instead of North Denton, we're actually adding a hub out at Alliance Airport. Now recharging. So again, the kind of the baseline number we've been using is what we heard yesterday, whereby we assume a 15-minute recharge time going from 20 to 90%. In line with what we heard this morning, we assume that there's a given reserve level of batteries. We actually used a 30% reserve, where I think it seems like it should be closer to 40. But we also played a what-if scenario if it took longer to recharge, either because of maybe there are queues that form, or other considerations. And what we really find is, sure, we serve fewer riders with slower recharging capabilities, but the drop in riders from doubling the recharge rate is pretty modest. It's within a couple of percent. So this is actually, I think, is very much in line with what we heard this morning when Professor McDonald showed a reduction in 2 flights per mission, always using this 5%, this 5-minute ground time to kind of top off. That's pretty consistent here. However, what they looked at was peak times. And so when it's off-peak times, then these utilization's lower, and we kind of get this recharging capability somewhat for free. So it's interesting that rider movement is not that much, throughput's not that much lower. Another thing that we like to track is what the battery capacity is of these batteries upon arrival, upon landing. And it really only significantly falls when the recharging rate's 30%. So in order to accommodate the loss of some vehicles, we have to deadhead more. We have to fly without any riders, which is shown in the bottom panel. There we're looking at the frequency of deadheads as a function of how many riders exist for one particular deadhead, for instance. So the needle doesn't really move that much here. So we kind of played another scenario, and we said, what if we permitted recharging capabilities only at our mega ports, Frisco Station, DFW? What we found naturally is a reduction in our throughput, but the reduction's a relatively modest 4%. There was really no difference with respect to the average passenger in terms of time saved. Naturally, these vehicles are landing with quite a bit less energy, but on average, they're still average. Even in this scenario, we're only permitting recharging at 2 stations, they're still landing almost always at above 50%. It's usually it's about 53% on average. The utilization's obviously lower because there are a few opportunities to charge. We're deadheading a bit more. Interestingly enough, we're getting more butts in seats, right? And we're doing that because a lot of the decisions about when to fly, we have to wait longer periods because we're recharging for longer intervals. And so that's providing us kind of batching opportunities where we can find more people to share the VTOL with. The next knob is trip volume. So I talked about the importance of the liquidity imperative, bringing the price down, getting more trips. So we did an exploration where, again, we're taking data from 3 days. And what we did is we looked at the exact same day, number of weeks prior to that, and then we would take the same timestamp, the same hour, minute, second, and then we would just kind of mock the date to simulate more liquid or a thicker eVTOL market. And so the question is, how much better can we do with more demand density? And so naturally, we are getting more butts and seats. With a 30% increase in trip volume, we're finding that we go from about 1.6 riders, 1.55, to a little over 1.8, which is pretty significant. So getting a thick market is important. Rider savings is better as well as we get more trips. Again, that's because of this liquidity imperative. We can be more selective and find more efficient matches to make. And again, these VTOLs naturally are flying quite a bit more when we have higher volume. This is still using that 40% benchmark value when in fact we might want to consider more eVTOLs. Next is the minimum savings. So what happens from a product perspective if we maybe deteriorated, if the rider experience was deteriorated to some degree. So now we're moving from a 40% threshold lower. So we looked at 35. So naturally, we deteriorate that. We require less savings. We can cover more riders, quite a bit more riders. So a 5% reduction in the minimum savings threshold is resulting in about a 25% gain in trip coverage, which is good. But there's that very fundamental trade-off between a quality of a trip from a rider experience and just covering more riders. So this is something that we hope to leverage our knowledge of other services, core services at Uber, like Uber Pool, for instance. And again, once again, as we require less of a minimum savings, we are getting more butts and seats certainly, yeah. So there's some very very salient product decisions that we are discussing very actively. So now we want to see how this performs in markets where the missions are shorter, half the distance, the minimum distance being half the distance. So let's consider now the Dubai network, and I'll save everyone the time. We're not going to go click through every single knob. So instead, what we want to do is just kind of focus on rider throughput in Dubai, much shorter missions. So one thing that's quite remarkable is that plateauing effect. How many eVTOLs do we need? It, like DFW, is about 40%, where it really starts to diminish in marginal riders served. We find a load factor, so we've done the exact same thing, where how many seats do we really need? And we find it's a little bit steeper from 3 to 4 in Dubai. So potentially it might make sense to have slightly larger vehicles. And the reason for that is almost certainly because Dubai, it's more concentrated, it's a little more geographically friendly, whereby the high traffic corridors are in a considerably smaller region. We find pretty much the same effect, very linear with respect to minimum ground time. The slope is almost identical to what we found with DFW. The gains in cruise speed, again, it's very close to what we found in DFW, whereby a 30 mile per hour gain in our cruise speed results in somewhere between 18 and 19% gain in passenger served, even in Dubai, where we're flying shorter missions. And again, we find the trip volume. What's interesting is it's a little more, it almost looks a little bit convex in one part. So if we can get substantially more riders, we can get substantially more riders. If we can get substantially more total requests, we see pretty incredible gains with respect to how many people are in these. We exceed 2 riders with 70% greater trips, which we think is very attainable. And also, very similar observation with respect to rider savings. So a deteriorated rider experience leads to approximately the same kind of dynamics of number of trips we can serve. Like the hub optimization case, we've run this in other cities as well. And for those who have read the white paper, the plot on the bottom right may look familiar, and this is kind of how we're rolling out hubs sequentially in other cities that we looked at, namely Los Angeles and London. Another interesting exploration. So again, remember that third thing I wanted to say is to try to identify conditions for which these networks can be healthy and sustainable. And one thing I talked about was just kind of liquidity. Again, bringing price down, getting more riders in. Another one is how to leverage kind of this whole intermodal aspect. So it's one thing to have, so the eVTOL is just one segment on a route. We also have this ground time from origin to departure vertiport, similarly from arrival vertiport to destination. So the question is what if instead, if we define savings, not to be from the time the car picked you up, but from the time you hit request? And so what we want to do is simulate a world where the Uber ground transportation network was less reliable. What if these ETAs, which is defined from when you hit request ride until the time the car picks you up, what if those were longer by 10%, 25%, or 50%? And naturally what we find is a considerable deterioration in the number of riders we're able to serve, as well as the quality of trips that we're able to serve. So we went over this, admittedly, fairly quickly, but I think the kind of the salient observations, first of all, is these networks that we showed yesterday and today, and hopefully you'll be seeing more shortly. These are not arbitrary. They're coming from well-informed data. We're very excited to work with our partners at SDG, who are going to be talking about, again, more intelligent modeling, which will lead, I think, to more robust solutions. And so we're very active in extending this work, but from a number of dimensions. One is to try to create more robust solutions. So we saw sometimes when you dial a knob on the VTOL, all of a sudden the hub networks they change a little bit. And so one thing we're really interested in doing is trying to create a more stable network, a network that's more robust to uncertainties. Secondly, we talked about kind of what some of these levers are. Most of these are actually quite intuitive. So I think 3 of the levers that are particularly valuable to us include the cruise speed, this MGT, minimum ground time, as well as just trip volume in general. We said that we probably need maybe 4 seats in DFW, 1 for the pilot, 3 passengers, and I'm sorry, this should be read as 5 seats in Dubai, 4 for passengers, 1 for a pilot. That's if the data scientist gets his way, at least. And these networks are dynamic. Again, I just wanted to emphasize the point that we need rigor here. Again, knobs can change outcomes, they can change networks, so it's very important to be really rigorous, to be very clear about the product decisions we're making, and so this is kind of just an introduction to this Flux Optimizer. So it's one thing to have the engine, it's another thing to use the engine. So I'm going to give it back to my friend and colleague John, who's going to talk a little bit about its usability.
All right. So it wouldn't be a design presentation if there wasn't one more thing. So this part's all about you, my users. Now, I'd like to introduce what we're calling Jetson, which is the front end to the Flux Optimizer back end that turns uncertainty into universal clarity. We're designing a tool that can be broken down into two main parts: user inputs and queried outputs. The first user input starts with a location. Next is a series of modules, like John mentioned, including hub config, hub optimization, VTOL config, as well as route optimization module with inputs covering everything from parking count to recharge times. Even operational curfew restrictions can be defined. After setting the date range, these user input variables create a query, run against Uber's trip history, showing the peaks and valleys of demand for that time period. The resulting output reveals optimal lat longs per hub type, along with flight paths between those hubs, with each vehicle's flight location indicated along those flight arcs. It also shows the number of VTOLs on approach to, departed from, or parked at each hub, along with the status of each vehicle's power supply. For the total network output, we can see the active fleet utilization, trip efficiency benefit over ground transportation, and total riders served at that particular moment in time. Together, we're designing this tool to fit user-specific needs for every market. The Jetson front end is currently under development, which will soon include airspace classes and the ability to manually add or remove hub locations to better understand its network impact. And we're excited to make this accessible to our partners within the Uber Elevate network. Thank you. Now I'll hand it over to David Cumio, and here you go.
Thank you, John.
All right, thank you.
All right. So I'm here from Steer Davies Gleave. We're a transportation consulting company that has offices around the world, and a major theme of our history has been doing travel demand studies for all modes of transportation. Here in the US, some of our major modes have been looking at proposed high-speed rail lines and looking at the traffic and revenue potential for managed lane facilities. So we're very excited to be working on this study, which is to look at using the information from the optimization, using the information about the site locations for the hubs, the routes that are going to be used, all that service information we're using to develop a demand model for potential Uber Elevate service. And so our first case is looking at this in the situation of Dubai, and we're developing this tool that then can be used to really understand what would be the true OD, origin destination demand for this type of service. What would be the throughput on the different routings that John talked about, and understanding at different price points what levels of demand we would get. So we're conducting this study over a 10 to 12 week period, and we've just started this study, and we've conducted our site visit in Dubai recently, just got back from that and getting started on our model development. So our model structure is similar to a travel demand model that we apply, our generic framework for applying this model, and it's got three basic elements. So first, we have to understand what trips are in scope for using this service. So this is where we look at all the trips that take place currently in the area, and we recognize that not all of them are really candidates to use this service. As mentioned yesterday by Jeff in his intro talk, a trip that's going to go 3 blocks is not going to be a candidate for using this service. Similarly, if the hub locations are in certain locations where you wouldn't have, it wouldn't be convenient for a traveler to use this service, they're not going to be in-scope trips. So we look at all the demand for the study area, and we figure out which of those trips are in scope for using this service. We look at it both today as well as into the future. And so when looking into the future, we'd like to understand where there's going to be development that will bring about new population and employment. And so we bring all that information to figure out what trips are in scope to using the service. And then we go to the second component where we figure out, of those in-scope trips, what percentage of those trips are likely to be captured by this new service. And so here we need information about the Elevate service itself, as well as the information for other transportation modes, what their travel times and costs would be, as well as information on traveler behavior, sort of how travelers value their travel time savings, what sort of preferences they have. And that comes together and allows us to figure out, of that in-scope traffic, what percent we are likely to capture for the Elevate service. And then finally, we generate the outputs from our model based upon that process. As you might have guessed, the capture component is very important in our modeling. And ideally, we would have some revealed traveler behavior that we could use to base this capture on. But as you know, it's a service that isn't in place yet, so there's no observation that we have of real revealed behavior. So while we might have thought about doing some original market research to understand how travelers say they would behave, we're not doing that for this study. For one, for the schedule being so short, but two, it's probably a very difficult thing for a lot of travelers to put themselves into that hypothetical situation. So rather, what we're doing to serve as the basis of our capture is using information that's specific to our study area, in Dubai in this case, understanding wage rates and some information from their travel demand model, as well as information on traveler behavior for other high-value modes. And one of the things we see, there are other modes. For example, managed lanes. We have a couple facilities here in the Dallas-Fort Worth area where travelers are paying a premium to get a highly reliable, faster travel service. And we could actually look at historical information on what time savings are, what toll rates travelers are paying on managed lane facilities. And that gives us some insight into how willing travelers are to pay for those sorts of premium services and travel time savings. And it's important, though, as we represent this in our model, that we don't use a one-size-fits-all in the representation of traveler behavior, but really we need to represent a range of behaviors. It's typical, as seen on the distribution of values of travel time savings, there's a range, and it's for a high price service, or when we're thinking about the introduction of the VTOL service, and it's going to be something at a higher price point, it's going to be those travelers on the tail, those with the higher values of travel time savings who are going to be more likely to use that facility. And so we're building this into our model so that we're able to reflect this range of travel behavior. So our model is going to be fed by a number of different information sources. Importantly, we have the tool that John just described, that location, hub location tool, is going to tell us all the characteristics of the VTOL service that we need to reflect in our model. But we also need information on the travel demand, the transportation demand, and the transportation supply for other modes in the study area. And so typically this is something that we'll be able to get from regional travel demand models for our study area. In the case of Dubai, we are working with the Roads and Transport Authority to get information from their travel demand model that'll give us that information on trips that could use the facilities, the VTOL service, as well as what are the times and costs for the other modes of transportation. Then that'll feed into our model, which we're building, and produce the outputs that will work with Uber in allowing them to make their decisions moving forward. We're conducting our study through scenario analysis, and we're going to start with an ultimate network. And this is, as John had talked about, where there's the candidate hubs, where there's a large number of potential hubs that would be in place. We would use a service characteristics in accordance with that. So we'll have all the routes that would be able to serve that. We would know travel times, and we would conduct our model, generate a base set of forecasts for that ultimate configuration. And then based on those results, on the throughputs, the demands that would use VTOL service in that scenario, we'll work, refine the network definition with a low number of hub scenarios, say, call it 10, and a high scenario, maybe 75. And then for each of those, we're going to look at both the base forecast as well as higher and lower forecasts to really develop a range for what the likely outcomes would be, the levels of uses of such a service when it's introduced. So thinking about the potential for this service in Dubai, Dubai already experiences large travel time delays on its roads during peak periods. Travel times can be double what they are during normal conditions. And this is all despite the fact that the population in Dubai is expected to nearly double to 5 million from its 2.5 million now by 2030. So there'll be a lot more demand, and as that demand tries to get into cars and taxis, the congestion on the highways is only going to continue to grow that much worse. So we see that population growing. We see that given the where that population and activity centers are distributed throughout the region, there's a lot of potential trips which could be in scope for using this sort of service. Already, there's a large volumes of taxi trips. If we look at one potential mode of transportation, which VTOL might be able to capture and shift from one mode to their mode, there's already a high level of taxi activity in Dubai. So unfortunately, we're just getting started on our study, and we don't have any results that we could share with you yet. But we're really looking forward to conducting our study, and hope we'll have an opportunity to share the results of our studies, our findings, before too long. So with that, I think I turn it over. Are we to questions?
Yeah, I think we do have the Slido going.
I've got more jokes.
More jokes?
All right, why don't I just moderate these there? All right, first question. Are you modeling specifically work trips or all classifications of trips? What market of trip types are you trying to serve with the Elevate?
I can try to take that. So I'll refer to this mission statement about trying to make Uber as reliable as running water. The second part of it was everywhere for everyone. So do we distinguish? No, we don't. But we do think that there might be a very interesting number of extensions. Maybe there'd be a premium service. People's ability and people's propensity to share a ride with others can vary drastically across not only individuals, but places, obviously. So are we modeling it? No, we're not. But you can imagine, again, going back to product implications, there could certainly be opportunities in the future to distinguish different products between commuters and others.
I could add to that. We do see in travel demand modeling that the value that people place on the urgency of their trip is not necessarily something that's strictly work versus non-work. We often see that it's people. You might have somebody not on a work trip, but needing to meet a daycare pickup by a certain time, or meeting some penalty for being late there. And so their behavior is not always necessarily based on their trip purpose, but actually more dependent on sort of the situation that they're at that point. And so we do, in a lot of our models, try to reflect the range in behavior, pulling it away from trip purpose, but more just based on the exhibited behaviors the range of behaviors that we see. The one other point I'll add here is that work trips, though, there is a way that we can draw and identify the value that those travelers might place on that trips. There's some good DOT guidance on sort of how you would value travel time savings for a work trip, looking at what wage rates are. And so I think it's useful information that we're planning to use in our study, but it's not only work trips which would likely use this service.
All right, next question. Do you think that self-driving vehicles will impact demand for VTOL? If SDVs can substantially reduce traffic, how would that affect VTOL demand?
Yeah, I think so. It's multimodal, right? So if we had self-driving capabilities, just imagine what the implications are from going to and from your vertiports. One, I think, very interesting question is, what about existing drivers? So suppose that we were at a network of 25 hubs. Presumably, the distance between, because we have this threshold in time savings, it's likely that you might be able to walk to a hub, but if you're unable to, then you need to go by car. If we had the ability to, one question is behaviorally, what are drivers are going to do? What if these trips all of a sudden are much shorter because they're going from your origin to a departure hub, which might potentially be considerably less than the median trip distance in that city. So with self-driving technology, that kind of some of these behavioral characteristics are not quite as present. Number one. Number two, the ability to bring down the cost of self-driving technology could potentially feed into lower fares for riders as well. So I think there's tremendous opportunity. We're incredibly excited about this.
All right, next question. Are you capable to give us an acceptable vehicle cost, NRC, DOC, with the tool?
If I want a job, probably
so.
not. Thanks for the question, though.
All right. We answered the top one. Here we go. Why is the minimum savings threshold set at 40%? If I could achieve a 20% time savings, I would like to have that option.
Sure. So again, we really focused on kind of a short and intermediate time horizon initially. It is potentially possible. I talked about segmenting the market, maybe permitting other options as well. One thing that I'm really interested in is what if we had a connection network? What if you could take an eVTOL from Frisco Station to DFW, connect, and then ultimately go to downtown Fort Worth? That might be of interest. Okay, if you're willing to reduce your time threshold, it's possible. It's just not in the product scope for a number of, I think, strategic reasons. It doesn't necessarily mean it will never be possible. One thing that is very important is to understand what the implications are with time savings in different cities and trip composition. And so we spent a lot of time arriving at that 40%, by the way. It's because we think that is kind of a number that can give us sufficient liquidity and create somewhat of a healthy network. But number two is, again, this notion of giving people time back. We want to provide a truly magical experience for our riders, and we could certainly wrestle with the idea of lowering that threshold. I'm not stating that when you actually press a button and get a flight that you're necessarily firmly going to save 40% of your time, but it's a number that we've been using, and we've looked at a lot of sensitivities, and in short, it kind of makes sense to us.
All right, next question. How do your traffic not only car sharing data, differ from Google Maps generated data? Can you enhance Uber data with Google data? Who asked this? So actually, I think I can chime in a little bit on this one. I think, especially in our mature markets, the Uber traffic data is at parity, and in some cases even better than what's available on Google Maps traffic data. I would say we do augment our data with any data source that's available to us in the interest of saving riders time and more efficiently pairing riders and drivers together. I think that's pretty much as we could say about that question. So what time span does the optimization model consider? The 3-hour peak period or a full day?
We've never run the optimization model with less than 1 day. DFW, we considered 3 days. This is a Tuesday through Thursday. Dubai was similar. I've run an instance where we looked at an entire month in Dubai, albeit for a little bit longer trip distances. We usually like to test weekends. I didn't present that, but we've run that same 3-day horizon. We've run it over weekends in Dallas. We've done it with when there are large events in town. There might be some subtle changes in the network and the throughput, but generally it's fairly stable across different time periods. That's not necessarily the case in all our cities. We ran it in another city in New York area, and naturally in summer months, you're doing a lot of trips to the Hamptons, you're going to the Jersey Shore a lot. That's very different. That can actually change. So yeah, it's flexible across different days. It's completely up to the user.
Cool. Does your model account for the impact of weather and/or maintenance delays?
That's a great question.
That's a great question.
We started this work not that long ago. No, we're cognizant of that. We are very, very keen to have greater fidelity modeling in terms of airspace restrictions. I mean, we'll do like the 1 minute, we'll do a minimum separation for simultaneous operations, certainly, but we are very eager to team up with others, particularly some from NASA Ames, in order to capture attributes about specific sectors, the throughput, maximum capacity. Recovery is something that's very near and dear to my heart. Unscheduled maintenance and convective weather, things of this nature, having worked on this in the airline industry before. And so that's winds. I mean, there are all sorts of operational disruptions. Does this model consider it? No. Will it at some point in the future? Absolutely.
All right. Have your findings on demand density caused you to find anything that would impact vehicle design? For example, minimum maximum cruising speed or holding time?
Yeah, so I mean, one of the things that we explored was kind of this holding time. So you can consider a longer holding time through either the minimum ground time or even the faster speeds, the faster cruise speeds. Faster cruise speeds mean, all else being equal, you reach your destination faster, you have more opportunities to hold. So absolutely, I think we've not only we've run a number of different instances. We've also looked at specific vehicle design. So for those who were in the talk at 9 a.m. this morning in this room, they looked at 10 different vehicle designs, from multicopters, autogyros, helis, coaxial helis, compound helis, lift and cruise, vectored thrust, tilt wing, tilt rotor. I'm missing one, I apologize. And so we looked at all of their attributes. We used the exact same assumptions. What we find is when we permit full charge capability at every single vertiport, it doesn't really become binding that much with respect to how things might differ with energy consumption. But again, if we reduce the ability to recharge, and if we only considered it at a couple hubs, then you get some very interesting, very different trade-offs between vehicle types, which we've explored. We really hope for this tool to allow us the ability to inform what like minimum specs will be. That's absolutely important. That's a great question.
Okay, next up, I noticed rideship numbers based on time savings. What about sensitivities based on cost, socioeconomic parameters?
Yeah, so I mean, our model also considers certainly other objectives. All of these, both the hub and the route model, consider all sorts of objectives. Right now, I really want to focus on moving riders, again, available everywhere for everyone. So we certainly have the ability to look at economic-based models, and we think we have pretty good parameters estimates around the operational cost of these VTOLs. We're starting to gain a little bit of understanding about how much it costs to build out the infrastructure. We have assumptions on what the vehicle costs are on eVTOLs, and so yes, we definitely have the ability to extend it and have extended it on other considerations as well, just beyond moving number of riders.
And I could add for our demand study, when we look at high and low scenarios, these are some of the factors that will be adjusting in those scenarios. We'll be changing the socioeconomics, what that base demand is looking like, whether it's higher or lower, the characteristics of both the VTOL and other modes, the cost of those. These are, and how travelers themselves perceive the time savings and behave in response to that. These are some of the attributes that we're going to change in our high and low scenarios, so we'll consider those.
Really like this next one. How do you model demand for trips that are not commonly served by Uber today, but become appealing once eVTOL is a reality?
I could talk about what we do. In the first pass, we're going to be conservative and not include those. But it's common in travel demand forecasting that you have this step once you've sort of looked from a given area, how many trips you have that originate there and how many are destined to those areas, that you piece those together through a trip distribution process into trips. And that process sort of goes, it's inversely proportional to the impedance that you have between those locations. So when you have a mode like this, which is coming in, is really making those places seem closer, you're going to wind up having a greater percentage of your trips tied together with these longer, further apart origins destinations. And so in the first pass, we're going to be more conservative and not adjust, but this is something down the road our demand model through enhancements can be adjusted to account for this, to reflect how more travelers would make these longer trips if they're that much more convenient to do so.
Great. For the DFW Frisco route, what is your maximum passenger throughput per hour that you're planning for?
So during peak periods, defined loosely rush hour, the utilization, so the numbers I presented formally are just kind of averages. If you disaggregate it into peak and off-peak, during peak they're flying nearly at 100% utilization. They're just constantly taking off and landing. It's a very popular route, particularly in the morning, going from Frisco Station to DFW. There's considerably less going in the other direction in the morning. And then that observation is obviously reversed in the evening. So what I'll say is one can back this out with that observation in conjunction with the number of seats we're offering. So we do have some separation requirement as well with respect to spacing the consecutive departures and arrivals. 1 minute.
Okay. Have you considered travel cost compared to ground network and done a logic model to assess demand? Kind of similar.
So have we done you want to take that?
Yeah, I mean, in our demand study, that capture element that we're going to do is going to take the form of a logit model. It's going to have the cost of all the modes represented, the travel times, the cost, and then these behavioral parameters represented in the utility functions of a logit model. So that's exactly how we're going to model that.
Okay. Doubling your infrastructure but only getting a 5% improvement in rider coverage, is this worth the development cost, rolling out infrastructure?
I believe that question probably pertains to the hub optimization model when I talked about rolling out DFW on the existing Hillwood network. Again, what I'll state is that it's kind of natural that with demand patterns, all else being equal, there's going to reach a point where you've satisfied about as much demand as you can. However, by acquiring new properties, by expanding out in other locations, there we get substantially greater trip growth. So I believe that question is referring to just the Hillwood network now. it is my hope and belief that the Hillwood network tomorrow will be different. It will be more diverse. And what I mean by that is, I mean hubs that we would build. We could, as I mentioned, if we added just 5 hubs beyond that Hillwood network, we obtain about 74% trip coverage. So that plateauing effect goes away. So it will be absolutely critical to make sure that we monitor the health of these networks as they roll out and as they develop, and to build out new properties when we are able.
Okay, are you looking at transit connections?
If transit connection means VTOL, take a layover, take another VTOL, I addressed that a little bit earlier. Are we looking at it? I'm very interested in that. This is something that Nikhil and I have spoken at length about. I think now we're talking point to point. Maybe in the future. I don't want to really make a claim one way or another on that, but it's certainly, I think, a very interesting and compelling framework. Looking at transit connections with other modes of transportation, just think of the ability to press a button, get a flight to DFW, and then get on your commercial flight. That's interesting. Jeff yesterday in his keynote spoke about how many of the Uber trips are on the last mile trips. I think that can be seen in Uber Elevate's network as well.
Yep. If cost is within reach, how do you handle overdemand? Dynamic pricing models could push it out of the range for the average Joe, creating a luxury service. Repositioning.
I think, I mean, if it ever gets to the point where during certain times of day the demand is far surpassing capacity, you might need to apply some sort of dynamic pricing to manage that demand. But I think if it's only happening during part of the day, what you might be pricing some people out of is just those peak of the peak periods, whereas it would still, if it's remaining that affordable, be there for the general population the rest of the time. And if not, then it's calling for that the demand is so high that there's probably that potential to go with a larger network with more hub locations and more routes being offered. And so I think, this is something that would happen further down the road, but I believe that there's probably ways to keep it. So if it's really that attractive and generating that much demand, it could still serve the large majority without being just a luxury product.
Yeah, two brief comments. Number one, if you reference the white paper, we have that route between San Francisco and San Jose, and there's a temporal aspect as well, right, where it's likely to be higher at first, ultimately driving down the cost over time. Number one. Number two is Uber is I think has a lot of experience in the art of dynamic pricing and revenue management. Naturally, it's likely that similar models would be present in an eVTOL network as well. There are a lot of very interesting questions when you try to think about pricing an itinerary when you have a ground segment, which should probably be composed of not only those riders that want to take an eVTOL, but what about the other riders in the network who are just going from point A to point B, pressing a button and getting a flight. So how to dispatch. There are all sorts of very interesting and very rich problems about not only pricing, but dispatch and other algorithms that are absolutely essential to Uber's core service.
All right, next up, what is composed in the price point to customers? Does that change depending on load factor?
It does. So again, lower price generally result in a higher demand, higher load factor. And the one thing I want to emphasize is that when demand can be stimulated, all else being equal, it's one thing to have higher load factor. It's another thing to have higher load factor with individuals who are going to a much closer place to where you're going relative to one who's going quite a bit farther away. So when you can get that, drive out that efficiency and ultimately bring down your cost, that can be passed on to riders as well. That's that flywheel effect that really excites us.
All right. Value of time is the highest for aviation and really low for commuters. What did you estimate for eVTOL commuters? Is that
Yeah, one thing I can say is so it's a little bit of an open question, obviously. So one thing we can do is we can leverage what we already know about Uber riders, particularly in ride-sharing services like an Uber Pool. So we have a very highly regarded marketplace team at Uber who we starting to partner with and kind of think about these time versus price trade-offs.
Have you considered integration flight path with local weather radar for storm avoidance?
Absolutely. I mean, I love the question.
We should.
I'd love to take this module. I'd love to integrate it with higher fidelity systems. This was work that began not that long ago. So this is something I think is very fruitful. There's considerable value, and I'd love to do this sooner rather than later.
Yeah, and I think actually something that comes to mind is as these vehicles become a reality and we could start to understand their ability to perform in different types of inclement weather, that would be something worth integrating as well per model. What have you learned not to do with Elevate based on observing the airline industry?
It's a great question.
That is a great question.
This is recorded? Okay.
Well, we have 16 minutes to answer.
Okay, so there are a lot of. It's a great question. I love the question. I just want to reemphasize this thing about product thinking. We've invested a lot in this technology, by the way. We've invested a lot in the tech. We have a lot of these product implications. It's a great question. It's one that we're trying to really understand our customers, obviously, right? I mean, airlines, they're very good at dynamic pricing. We are very good at dynamic pricing. I think it's to give. What I want to say is I'm just going to take the easy way out. I'm going to say it's an open question. This product decision we're trying to be very very careful with, and it's slowly evolving. There are a couple things that come to mind, but I don't want to state one thing and turn out to be another. So what we want to do is we want to give, again, I just want to reiterate that we want to give people their time back. There's considerable value there. So we want to make this as efficient as an operation for individuals. And I guess the one thing I'll say is I'm sounding like a broken record now, but available everywhere for everyone. And so if we can serve underutilized cities or regions, I think there's considerable value there. We hope this network is able to kind of expand the reach beyond just urban city cores.
Yeah, and I think part of that is about keeping the planes in the air.
Yeah.
Right? Because
Right.
you can't serve everyone if your planes are on the ground.
Yeah.
Does the model account for troublesome passenger behavior and/or security issues? If there's a problem, does the whole network go down?
So irregular operations, it's a very salient point of this kind of product thinking decision. It is one where we are not living in that environment right now. We're not unaware of it, certainly, but right now we have not. I'm very interested in that, though. Security is I think some of the nuanced details about security, I'll let the security experts answer that. But I think initially we have not.
Have you begun working on a day of operations optimization model where requested trips are probabilistic, changing as the optimization algorithm runs?
Yeah, I mean, so right now what we're doing is we're conducting a tool that can help us inform various attributes. There's another problem about actually dispatching in real time. I'm not asserting that this is a tool that one would use in real time, largely due to kind of the combinatorial nature of it. However, yes, so these questions of how would we actually dispatch, when do we actually decide to depart, to schedule a departure for an eVTOL, this is a little bit different question. This is more of an operational question. So we are certainly aware of the perils of making a decision based on an assumption when the number of possibilities are very, very large. So what we do want is we want to be robust. Right? We want to make decisions that are somewhat amenable to uncertainties. And so, yeah, so when we dispatch cars, when we price, all of these come into consideration.
Would you consider publicly releasing a representative demand data set to crowdsource network modeling ideas? Not sure. I don't think we're going to answer that one. Is there a bundled cost for taking the Uber to the vertiport and then taking the VTOL? I think that's a good one to think about.
Yeah, I believe it'll be surfaced in an upfront price, my belief, and of course that will be influenced by the kind of the marginal cost attained at going from your origin to your departure vertiport. Certainly the state of the eVTOL network, where the aircraft are now, where they will be upon arrival. Certain demand patterns. So you're going from DFW to Frisco Station in the morning. It's likely that the value of that route, that direction, is very different from the direction that's going inbound, particularly with commuters. So I think you're going to see that, but I want to reiterate that it's a function of a number of processes along a VTOL itinerary.
Where's the role of air traffic control, especially in the beginning when VTOLs will be human piloted, and in a system such as DFW that is already overburdened?
Yeah, we're very active in this, in working and collaborating with our partners in aerospace, and so this is something that is going to evolve as well. Right now, the air traffic considerations are fairly minimal. We do have minimum hub separation. We do have sequential flights separation, but things like airspace sector capacity, alternate like flight plans, all of this we're very active in developing and extending the V0 of our model.
All right, I think that's fair enough, and we'll give you guys 11 minutes back to go stretch your legs.
It's under 40%.
All right, thank you.
Thank you.